Alright, 110, last section for chapter 1. This is it. So mathematical modeling and variation. So two kind of separate things going on here. We'll start with the mathematical modeling and then we'll get to the variation. So first thing, we want to, in our first problem, just be able to once again put data into our scatter plot and then put an equation on there. They give us this linear model here. And then go ahead and see if that model matches the actual data. So let me bring up the graphing calculator and we'll go to plugging some things in. So I'm going to go clear my lists. So again, go up to L2, hit clear and enter, and clear and enter. And let's plug this in. So we'll make 2000 year 0, so 0 all the way to 7. And then L2, punch in those numbers. And I've got a little keypad here that's making it go a little faster than probably yours is. Anytime we'd have much more data than this to deal with, we'd start using computers and Excel really to punch these out. But the calculator is a nice place to start. So we've got that in our scatter plot. Let's go into our y equals. And they said our equation here is 2.78t, which we'll use x, plus 282.5. There are restrictions there actually, so let me go back up here and put the restrictions on it. So insert a parentheses, and we'll go to the end, and close my parentheses, and then I'm going to have to do compound inequality here. So x is greater than or equal to 0. X is less than or equal to 7. So I've got my restraints on there, got the line, and again, let's make sure our scatter plot shows up. So I'll turn the plot 1 on, and let's go ahead and graph this. And why is it not showing up? If you said my window's no good, you are 100% correct. What would be a good range? Minimum, -1 to 10, that's pretty good. The y's is way off. Smallest y is here, so how about 280? And the biggest y is 300, so how about something like 310? 305 would work, anything close. And there we go, we got all our dots, and we got our nice line, and boom, that's hitting them very, very nicely. So how closely does the model represent the data? It represents it almost perfectly, right? Very close. All right, so this one worked out really, really nicely. Try exercise 11 and see how well that one works. All right, let's talk about least squares regression and graphing utilities. So least squares, what our job here is, if we have a scatter plot and we have some dots all over the place, our job for a least squares regression is to try to figure out the line that lies closest to all the points. So the distance from those dots to this point to this line would be smaller than any other line that we could draw. All right, so we're going to use our graphing calculator to help us find that line. All right, so here is our data. So let's jump over to the calculator and plug that in. So it's 2000 to 2007. So if I go into my list, my L1 is already good to go. I'm going to clear out my y's and get the new y values in there. So 7, 7.7, 8.5, 9.5, 10.6, 11.8, 12.9, and 13.8. All right, got all my data in there. So if I was to graph it, let's make sure our window is good, maybe 5 to 15. And let's clear out our old equation and just make sure the plot's on. There's my dots right there. So our job is to find the line that fits those the best, and we'll let the calculator do this for us. So this is a statistics thing, so we're going to hit the stat button. And instead of entering things, editing things, we're going to calculate things. And so since back on our graph, this looks like a straight line, a linear line, we want to do a linear regression, number 4. So I'll go down to 4, or I could have just typed 4, hit enter, and boom, right there, think that's already up. Yep. I hit enter, and then it gives me my values here. So A, my slope at 1.007, if I was rounding, plus 6.7. So now I can go in and draw that by punching it in for my y1, 1.007x plus 6.7. Go ahead and graph it, and there's my line of least regression going nicely through all of the dots. All right? So that's what you would do here. Tell me the equation and draw a little scatter plot. See if you can do that for exercise 17. All right, so now we're moving on to variations. So there's a couple different things here: direct, inverse, and a combination of all these things, which we'll get to, but we'll start with direct variation. Direct variation is if we're just a straight multiplier of something. So we're going to go through the origin, right? No change, just a straight multiplier. So things like income tax is just a multiplier. When you buy something, they charge you a percent. They don't add any set fees on, right? You don't say, give me an extra $5. You would say, give me 7% of what you're buying. All right, so if we want to find that, we can do direct variation. This right here is our formula for direct variation. Y equals some multiplier k of x. All right, so let's go in and try this. You're working in Pennsylvania and your state income tax deduction is $46.05 for a gross monthly income of $1,500. Find a mathematical model that gives the Pennsylvania state income tax in terms of gross income. So in terms of, right, we're going to say income tax in terms of the gross income, right? So gross income is our x, y equals something x in terms of x. That's how I know that the gross income is x, so that's 1,500 with a k. And I know that this was 46.05, and so we would divide both sides by 1,500. And I don't have my calculator on me, so let's go plug that into this calculator. 46.05 divided by 1,500. So 0.0307. So that would be 3.07%. And that equals k. That's our multiplier. All right, so that's an example of direct variation. See if you can do that for me on exercise 43. All right, let's talk about direct variation as an nth power. So now we're going to throw an exponent on there. Same exact concept, but now it's exponential as well as being direct. All right, so we'll use this formula. And so the distance a ball rolls down an inclined plane is directly proportional to the square of the time it rolls. I'm just going to write as I read. The distance is directly proportional, so k to the square of the time it rolls, t squared. All right, so there's a. That's our equation. Distance is proportional. Proportional, I throw the equal in there, and the k. All right, as soon as I see proportional equals k, and then the square of the time. Okay, so b, how far will the ball roll during the first 3 seconds? Let's find the distance. Skipped a step here. We know one setup, so we got to plug that in. We know that after the first second, the ball rolls 8 feet. Okay, so a distance of 8 is what we get if we plug in 1 for time. So let's solve for k. So luckily, it's just 1k, so 8 equals k. So now we can figure out how far we'll roll after 3 seconds. So let's find the distance. We know k is 8 now, if the time is 3. And so now we can just solve algebraically. 8 times 9 is 72. Okay, so input 3, we get out 72. See if you can do that for exercise 75. All right, how about inverse variation? This is the reverse of direct, which means the more something goes up, the more the other thing goes down. It's like your old seesaw when you were a little kid, right? So the more you eat, let's see, no, that would be direct. Let me think about this for a second. Why don't you think about it? See if you can come up with an inverse variation example for class. See if you can think of something where the more you do one thing, the more the other thing goes down, right? Inversely related. Anyway, while you're thinking about that, here's our formula, y equals k over x. And so let's see if we can solve a problem. A gas law states that the volume of an enclosed gas, so I'm just going to write as I read, volume varies directly equals k as the temperature, and inversely, boom, I'm putting a divider as the pressure. Okay, so just as I read, that's what I would write down. So that's part A. Here's our equation. And for part B, we need to figure out K. We've got to figure out this constant term here. All right? So it gives us some figures. The pressure of a gas is 0.75. So 0.75 is on the bottom per square centimeter when the temperature is 294. 294. Okay, and the volume is 8,000. All right, so we need to solve for K there. So let's grab that calculator again. And so we're going to say 8,000 times 0.75 divided by 294. K is 20.41. All right, so now for part B, they say find the pressure when the temperature is 300. So we know that K is 20.41. Temperature is 300 Kelvin. And the volume is 7,000 over P. All right, I'm going to rewrite this as 7,000 P equals these two things multiplied together, and then I'll grab the calculator and we'll punch this in for an answer. So 2041 times 300, and we would divide by the 7,000 there to get P by itself. And so the pressure is going to be 0.87 instead of 0.75, so it went up a little bit. 0.874 is what we would get for our answer here. All right, see if you can do the same for exercise 77. All right, last one here, joint variation. So now we've got a multiplier, but it depends on two separate things happening. Z is affected if x changes and if y changes. K is going to be our constant, staying the same. All right, so simple interest. Simple interest is something where you're going to make more interest if time goes up or if you started with more principal, right? So we're jointly, let's read it right as we read. Simple interest, I is jointly proportional, so K, and I'm going to have two things, to time and to principal. Jointly jointly proportional means I'm going to have two multipliers. All right, so there's our equation. Find the interest after 3/4, so we've got to find K first. After 1/4, 3 months, so my time is 3 on a principal of 5,000. Got to find K. Our interest was $43.75. Let's find K. $43.75 divided by 15,000, right? 3 times 5,000. 0.0029 equals K. And so now let's find the interest after 3/4. So that's going to be 9 months. All right, so we want to find the interest. We know that the K is 0.0029. 9 months now, and on the same principle, $5,000. So we're just going to plug them in, multiply it all the way across. You know what? Let me keep this exact. Let me go up and grab it. Oh, it doesn't work on this graphing calculator. Sorry, so I'll have to plug it in. 0.0029 times 9 times 5,000. And there's how much money we'd make, $130.50. Which makes sense. That's about 3 times more than this, but it's a little bit bigger than 3 times this, because we know that as time goes by, our interest is compounding exponentially. Okay, it's getting more and more. So it should be a little bit more than 3 times that. All right, so your last one to try is 79. Figure that one out. Check the answers in the back of the book. Questions, please ask me in class.